Welcome to Introduction to Manufacturing. Today we'll be covering how we will manufacture components that will undergo metal forming and sheet metal working manufacturing techniques. There's two methods for metal forming, and the two methods are bulk deformation and sheet metal working. Under bulk deformation, we have rolling processes, forging processes, extrusion processes, wire and bar drawing. And then we have sheet metal working. We're working the metal to create components. For example, bending operations, deep or cup drawing, shearing processes, and miscellaneous processes. So the way you can remember this is that in bulk deformation processes, we're trying to create deformations of the body of the material that will involve the volume. With sheet metal working, we're trying to manufacture the part by bending or creating some sort of process that maintains the relative thickness fairly constant, but not quite. So now when I look at the fundamentals of metal forming, there's a large group of manufacturing processes in which we're using plastic deformation to our advantage. And we're using that to our advantage to shape the metal workpieces. Typically, when we do metal forming, we employ something called a tool, which we usually call a die. And what these tools do, they apply stresses that exceed the yield strength of the material. By exceeding the yield strength of the material, we can achieve the plastic deformation required to shape these materials into place. The metal takes a shape determined by the geometry of the die in many cases, not always. Stresses need to be developed to get into a plastic zone. And usually to plastically deform the metal, we have to apply compression stresses, and we'll see some examples of that will be rolling, forging, and extrusion. However, there are some forming processes where we need to stretch the metal, like bending the tube. One side of the tube will be bent and it will cause tension, and the other side of the bend will be in compression. And then there's other processes that we apply shear stresses, and we'll look at some of them. Material properties in metal forming are very important. The desirable material properties that we're looking for to achieve good metal forming is low yield strength and high ductility. By having low yield strength and high ductility, it will be easier to create the part by the metal forming formulation. These properties are affected by temperature. Ductility increases and yield strength decreases when temperature is applied. So anytime we use temperature, we use it to our advantage so that it's easier for us to bend the material or form the material, because when you increase the temperature, the yield strength decreases, making it easier for us to plastically deform the material. And also, we can also increase the ductility and not get into the danger of brittle failure. Other factors that involve the manufacturing processes of metals is strain rate and friction. When I look at bulk deformation processes, what we're looking for is massive shape changes that are caused by significant deformations. And when we say bulk, that refers to the work parts with relatively low surface area to volume ratio, which is quite different from sheet metal working. And again, low surface area to volume ratios like you see on the right here is called bulk because it's voluminous. And then you're looking at starting work shapes, including cylindrical billets and rectangular bars as an example. Rolling is what we're going to talk about now. When you look here, the basic bulk deformation process, rolling. So here I'm applying a force to this workpiece. This is a workpiece I'm trying to form. And as I feed it into these rotors here, and you can see the rotation here depicted by these arrows and some velocity, you'll start to see that by rolling this material, we're changing the thickness, which is the desired property here. With forging processes, when I have this work material, what I'm trying to do is I'm trying to use these dies or these tools to apply a force down that die at some velocity, and that's going to cause the work part to take form. And we call that forging. In extrusion in this case is where I'm applying a force to the part through a ram, and this ram pushes the work material, which then through the die, we're extruding the material out. We call this metal deformation process extrusion. And some of these ones we see in polymers too, to some extent. The wire and bar drawing, very similar to the extrusion, except here I don't have a ram, I have the work material, and the work material is pulled instead of pushed, and that's going to allow me to pull the material through the die at some velocity, and that's called drawing because I'm pulling it rather than pushing it. Here I'm pushing it through a die, creating the material called extrusion, and then here I'm pulling it, I'm drawing the material, and this is one of the processes we use to create wires and other types of bars. When I look at sheet metal working, I'm looking at forming and related operations that are performed on sheets, strips, or coils. Those tend to have high surface area to volume ratio of the starting metal, so a lot more surface area compared to volume, and that is what distinguishes it from the bulk deformation process. They're often called press working because of the because we press the parts to create the operations, and these parts are called stampings, usually using tooling and punch and die. Here I have the example of a sheet metal bending process. I'm applying a force here, and this is my work material, and this is called a punch. And you can see how this force is applied to this punch, which pushes on the work material onto the die. You can see that this has large surface area compared to the volume, and that's causing the work part to be bent into shape. With deep cup drawing, we also call it, in this case, drawing as well. So here I have the die, here I have the work material, and here I have the punch. So here, this punch is pushed down, and the blank holder is keeping the work material into place. And as I do application of the punch, it pushes onto the work material to form it into that die. Very similar to this one, but this slightly different in that I have this material here, which are called a blank holder to keep it into place, while here I have that work material and apply the punch downwards. So very similar, not very different from this one. And so now I have the sheet metal application here, where I have this shearing action that we're going to be applying. I have the die here, the work material, and the punch. And you can see here that I'm going to apply a load in this direction to call shear. This is called shearing operation. So what am I looking at here? One of the things I need to discuss here is the material behavior in the metal forming process. So we're going to take advantage of the plastic region of the stress strain curve. We've learned already that the stress strain curve has a linear region that goes up to the yield strength, and from there you have some amount of nonlinearity associated with the material, has energy under that curve that we can take advantage of. And this stress strain curve is going to help us understand what's going on. In a plastic region, the metal behavior, you can simplify it by a flow curve. Let's say it's stress equals K times epsilon to the N. Here, N is the hardening exponent, K is the strength coefficient, and these are constants that we can use to try to fit the stress strain curve. The flow curve here tends to be as a function of true stress to true strain. We talked about it earlier, where true stress and true strain are based on the current loading conditions and the current cross section and the current length as I'm applying loading to that specimen. So when I apply higher and higher temperatures, you can see how the stress strain curve changes. Not only increase the ductility, I also decrease the yield strength. So any metal, this K and this N will change as applied temperature. Both K and N will be reduced at higher temperatures. And not only that, I get higher ductility. So any deformation operation can be accomplished with lower forces and power at elevated temperatures. And we want to take advantage of that. Three temperature ranges in metal forming are cold working, warm working, and hot working. So there are three ranges we look at typically. In cold working, we're performing these operations at room temperature or slightly above. Many cold forming operations are important mass production operations because we can make them very quickly. We can make parts fairly quickly. The beautiful thing about this cold working process is that the parts that come out are near net shape with very little machining required and very little waste generated. The advantage of cold working is that there's better accuracy, closer tolerances, better surface finish because I'm not really touching the surface, and the strain hardening does increase with strength and hardness. The grain flow during the deformation can cause very nice directional properties in the product. So as I'm bending the material through a cold working process, I can achieve very nice properties. There's no heating of work required. And remember, I want to remind you that cold working is part of the metal forming process that we talked about. Okay. So again, there's three ways that we can do the metal forming: cold working, warm working, and hot working. So yeah, cold forming also has no heating required, which is also very nice in terms of power requirements. Now, the disadvantage of cold working is that because I haven't applied a higher temperature, the yield strength will be higher and is more brittle too. And I also have a higher strain hardening. So what does that mean? It means that it will be more difficult to apply the forces. Higher forces will be required, more power is required to achieve the deformation required, and the surfaces of the starting workpiece must be free of scale and dirt. Otherwise, there'll be some issues with that, with the part. Ductility and strain hardening limits the amount of forming that can be done. Because I have not really increased the ductility, I need to be careful that when I'm applying the loads to manufacture the part, I'm not going to fail it by brittle behavior. So, in addition to that, there are cases where the metal is must be annealed to allow further deformation. So that means I'm going to have to heat it up to some level to allow more deformation to occur. With hot working, what I'm doing is I'm doing deformation at temperatures above the recrystallization temperature. The recrystallization temperature is about one half of the melting point in the absolute scale. So in practice, hot working is usually performed somewhat above zero point 0.5 times the melting temperature of the material, and the metal will continue to soften as the temperature increases above zero point 0.5 times the melting temperature of the material, and that will allow us to enhance and advantage and take advantage of the hot working above this level, because now when I do hot working, I am increasing ductility, I am decreasing low, decreasing the strength, the yield strength, allowing it to more easily apply loading. So why hot working? Because the capability for substantial plastic deformation of the metal is far more than possible with cold working or warm working. So I just described it, but the strength coefficient is less. The strength hardening is near zero. And so the ductility is also significantly increased. That allows me to be able to very easily deform the material. The advantage of hot working is that work part shape can be significantly altered. So you can actually make very large changes to the part. Lower forces and powers are required. The metals that usually fracture in cold working can be hot formed in this case. So if the other ones didn't work, but these ones can work. And then the strength properties of products are generally isotropic. So you don't have the orthotropic behavior we saw with cold working. No strengthening of the part occurs from work hardening, so it's advantageous in cases where when the part is to be subsequently processed by cold forming. So very nice here. Then the disadvantage is lower dimensional accuracy, is more difficult to control the dimensions, higher total energy required because you need to apply thermal energy, but also you can get surface oxidation, which can lead to also poor surface finish. And also because of the heating applied, the tooling can also have a shorter life. With warm working, you're looking at performing the operations at temperatures above room temperature, but below the crystallization temperature. That means that this is the dividing line between cold working and warm working. You're looking at between 0.3 times the melting temperature to 0.5 times the melting temperature. And here we're looking at the absolute scale, by the way, kelvins. So the advantages here, lower forces and power to produce the operation compared to cold working, but it's still hot working still is better in that case. More intricate work geometries are possible. You may need to anneal, but in many cases, the need for annealing is reduced or eliminated. Now, when I look at the strain rate sensitivity, theoretically, a metal in hot working behaves like a perfectly plastic material with N equals zero. So these metals should continue to flow at the same flow stress. So once that stress is reached, that stress will stay constant. You're not increasing the stress anymore. However, an additional phenomenon occurs during deformation, especially at elevated temperatures, and that's called the strain rate sensitivity. So what is strain rate? The rate in which the material is strained, directly related to the speed of velocity. So the deformation speed V is the velocity of the ram or other movement of the material. So I can take the strain rate and define it as the V, the velocity, divided by, in this case, the height, in this example, where epsilon dot is the true strain rate, H is the instantaneous height of the workpiece being deformed. So I can evaluate the strain rate in most practical operations, and the value of the strain rate is complicated by the work part geometry, variations in strain rate in different regions of the part, meaning there might be parts where the strain rates may be different from other locations. The strain rate can reach 1,000 per second in some metal forming operations. So flow stress so the effects of strain rate on flow stress is a function of temperature. At hot working temperatures, flow stress are also dependent on strain rate, and as the strain rate that increases, the resistance to deformation increases. This effect is known as strain rate sensitivity. I'll repeat again. So as the strain rate increases, there'll be a resistance to deformation as well. And so this effect is known as strain rate sensitivity. You can see the effects of temperature on the flow stress, and then on the x-axis, you can see the strain rate. On the y-axis, you can see the flow stress. So you can see at room temperature, almost no sensitivity. At 400 degrees C, you can start to see sloping here, which means that at lower strain rates, the flow stress is lower, and at higher strain rate, the flow stress is higher. So there is a sensitivity to strain rate that needs to be understood. The effect of temperature and flow stress for a typical metal is what you see here. The constant C, as indicated in the intersection of this plot with this vertical dash line, is what we call the value of strain rate at 1.0. And you can see here the behaviors of flow stress with strain rate. So again, what is it I'm trying to convey to you is that as the strain rate increases, there'll be resistance to the deformation because the flow stress is increasing. The other issue that we need to understand is the friction in metal forming. In most metal forming processes, friction is undesirable. Metal flow is retarded, forces and power are increased, tooling wears faster. And so those are the three things that we don't like because it's a problem. Friction is a problem. Friction and tool wear are more severe in hot working. Now, if I apply lubrication in metal forming, we could do that. Metal working lubricants can be applied to the tool work interface in many forming operations, and that'll reduce the harmful effects of friction. The benefits you get with that, you have less stiction, less forces, and you can also have less power required because now friction is not causing any resistance. The tool wear is less also. The surface finish becomes better, and also it does help with heat being removed from the tooling material. When I look at the bulk deformation processes in metalworking, we covered each of this. So we have rolling, which is squeezing between opposite roll. We saw that. Forging, which is the work part is squeezed and shaped between opposing dies. We also saw that. And the extrusion is the work part is squeezed through a die opening, and then you extrude the material through the die, so it takes the shape of the opening. And then we talked about the wire and bar drawing, which is I'm drawing the wire or the bar by pulling it through the die opening. So when I go to rolling, what I'm gonna do now is go in a little more detail. So this is the direction of the flow. I covered it earlier, but a little bit more deeper here. The deformation process here for rolling, you're taking the work thickness and you're reducing it by these compression forces that are exerted by these opposing rolls. And so now what I'm doing is reducing the thickness, as you see here. So the rotating rolls here that you see perform two main functions. They pull the work into the gap between them, and then by friction between the work parts and the roll, and they simultaneously squeeze the work to reduce its cross section. So they have two main functions there. Now there's types of rolling when it comes to this stuff. Flat rolling, which is based on the workpiece geometry, and then shape rolling, which is also based on the workpiece geometry. With flat rolling, you're using it to reduce the thickness of the rectangular cross section. With shape rolling, the square cross-section is formed into a shape such as an I-beam. So with based on work temperature, hot rolling is the most common because you can apply large deformations. And with cold rolling, produces finished sheet and plate stock. So let's look at rolled products made of steel. Some of the steel products are made in a rolling mill. And you can see here what it looks like in intermediate roll form. So I have the bloom here that's shaped in these structural shapes like rails and I-beams. Slabs can become plates and sheets or coils like this. Billets can become bars and rods. So here I have a diagram of flat rolling. And you can see here that I have a roll speed, VR. Here I have the angle theta, where it contacts here. And then here's the tangent. You have also P, the roll pressure that's been applied. And then you have the roll radius, because this is the roll radius here, this R. This velocity V naught, and then T naught is the initial thickness, and the V naught is what I'm feeding at what velocity. Here, this VR is the same as the roll speed here, and this L is the contact length. Here's what you see as the final velocity and the final thickness. So what you see here is that's a side view, and it shows you how the different features come into play to create that flat rolling. The peak pressure occurs somewhere between the entrance and the exits. So somewhere here at this location, and you can see that pressure is increasing from left to right and then drops again. So that's throughout this whole section here. So in flat rolling terminology, the draft is the amount of thickness reduction. So here I went from TF T naught initially to TF. So the final thickness subtracted from the starting thickness, that's called draft. And the reduction can also be looked at as the fraction of the starting stock thickness. So if you took D, which is the difference between the original thickness to the final thickness, divided by the original thickness, gives you the reduction. And so that's another formula that people use, generally speaking. And here's some formulas that may be useful to learn about, but there is a limit to the maximum possible draft. So this D here, that can be accomplished in flat rolling. And that's given by the coefficient of friction. D max is mu squared times the radius of the roll. You saw here, R, roll radius, where D max is a max draft, mu is a frictional coefficient, and R is a roll radius. So there is a limit of what can be accomplished based on this formula. So the shape rolling work is deformed into contour cross sections rather than flat. They're accomplished by passing work through the rolls, and then products include I-beams, L-beams, U-channels, and things like that, like rails for rolled trucks. Here you can see a rolling mill for hot flat rolling. The steel plate is seen here glowing in that process. So rolling mills, equipment is massive and expensive. Rolling mill configurations come in several kinds: 2 high, 3 high, 4 high, cluster mill, and tandem rolling mill. Here you can see the 2 high rolling mill. Here I have 2 rolls that we saw earlier. And then now I have the 3 high rolling mill. So what you see here is that this piece goes through a rolling operation, but then goes into a secondary rolling operation here. You can see that with a third roller. And then you can now also have a 4 high rolling mill that facilitates thinning the material even further. Cluster mill also, we have a situation where we have multiple backing rolls, and these rolls allow even smaller roll diameters to be used. And then here on the right, you can see Tandle rolling mills, which is a series of rolling stands that can be used to thin the part as it goes from roller to roller. So again, this is very nice because for all these conditions, like this one, for example, I'm able to achieve a smaller thickness, and then here I can achieve even a smaller thickness, and here I can achieve smaller thickness by going through a sequence rolling this one in sequence over and over. Thread rolling is a bulk deformation process used to form threads, and they're used quite a bit. They are important for commercial processes to make bolts and screws, and they're performed by cold working in thread rolling machines. The advantages over thread cutting is you can make many of them, higher production rates, better material utilization, stronger threads, and better fatigue resistance due to work hardening. And what you see here is the fixed die and the moving die. And they have the starting blank with no threads, and I put that here, and then I am able to push it through this right here, this moving die, which then causes this finished part to have threads. Ring rolling is a deformation process that's also used, and that's used to, for example, create ball bearings, the tracks for them. The deformation process is one in which a thick wall ring of the small diameter is rolled into a thin wall ring of a larger diameter. And you can see the operation here on the right. I am creating using rollers to create thinner parts. The advantage of this is material savings, ideal grain orientation, and you get the strengthening that cold working gives you. So those are the great things about it. Here you can see the edge rolls also creating some amount of deformation into the part. And then I have, so I go from here, and then this is the completion of the process. So this is causing the part to be stretched and also thinned. So this is the same part as this, and we're able to accomplish several things here. Forging is a deformation process in which work is compressed between two dies. This is one of the oldest metal operations that go up to 5000 BC. Components include a lot of different engine components, connection rods, gears, aircraft components, jet engine turbine parts. And here you can see open die forging, which is the work compressed between two flat dies, allowing the material to flow laterally with very minimal constraints. The impression die forging, in this case, you have a situation where each side of the die has a shape. And as I push that die against the part, I'm able to achieve a shape. In this case, the metal flow is constrained, and then so a flash gets created due to that. Now here you get a flashless forging. The work part is completely constrained in the die. So in this case, there's no excess flash created. Everything is contained in here very carefully. So going back to the open die forging here, that's a compression work part between two flat dies. It's similar to compression test when work part has a single cross section and is compressed along its axis. In other words, there's a test that people do where they take a part and they compress it to understand the properties. So this is what that's trying to say. The deformation operation reduces the height, but does increase the diameter of the work. And then common names for this is called upsetting or upset forging. So here you can see what's going on. I have an initial diameter, initial thickness, and as I compress it, the diameter is increasing, right? That's partial compression. And here's the final size with fully compressed, and you can see the diameter is larger with a smaller thickness. The open die forging with friction is going to cause some issues where, and maybe that's what you want, like a barrel, but that's going to create a rounding on the sides like a barrel because this surface is not allowed, it's stuck. So it's not allowing expansion along those surfaces. We call this barreling. Now this may be okay if that's what you want, but it may not be desirable always. With impression forging, which we talked about it, the compression of the work part by dies with inverse of the desired part shape. So you're going to try to have this die here that's going to have a reverse shape of what you need. A flash is formed by the metal because it's going to flow beyond the die cavity into the small gaps because there's a gap here. And as the part is compressed, you may need to trim the flash, but it could serve an important function because as flash forms, the friction resist continuous metal flow into the gap, and that's actually helpful. It constrains that metal into the die cavity. In hot forging, however, metal flow is further restricted because you have these dies and there's cooling occurring here on the edges. Impression die forging practice, there's several forming steps that are required with separate die cavities for each step. The beginning steps redistribute the metal for some more uniform deformation and desired metallurgic structure in subsequent steps. The final steps brings the part to the final geometry. The impression die forging is often performed manually by a skilled operator under adverse conditions. So what are some of the advantages of this approach compared to machining from a solid stock? Higher production rates, less waste material, like I said before, greater strength, and great grain orientation. That can give you great properties. The limitation is not capable of close tolerances, and you may have to do machining because of this flash that we talked about that is formed. You don't want that extra excess here, potentially. Now, with flashless forging, does not allow for flash. the starting work part volume must be equal to the die cavity volume because you're going to have everything filled, like you see here. It controls more demanding operations than impression die forging, and then best suited for geometries that are simple. These are often classified as a precision forging process because you can achieve high precision. Here you can see the part. I compress it, and this is going to fill all the cavities nicely. Forging hammers, drop hammers, you apply impact load against the work part. And there's two types: gravity drop hammers, which is high impact energy from a falling weight; power drop hammers that accelerate the ram by pressurizing air or steam. The disadvantage: impact energy is transmitted through the anvil into the floor of the building, so that can be a problem to the building, and it's commonly used for impression die forging. And here you can see a diagram showing the details of the drop hammer, and you can see how large it is. You can see the piston rod and the head that contains a cylinder, and the ram and the anvil. And so when you drop forging hammer approaches are used, they can be quite intensive in power and size. Now here you can see a human very small compared to the forging press. You apply gradual pressure to accomplish that compression operation. There's three types: mechanical press, which converts rotation of the drive motor into a linear motor of the ram; two, hydraulic press, which is hydraulic piston that actuates the ram; and three, screw press, which is a screw mechanism that drives the ram. And so we already covered the upsetting and heading, but talking more about it, a forging process is used to form heads of nails, bolts, and similar hardware products. More products are produced by upsetting than any other forging operation. It's performed cold, warm, or hot. Wire or bar stock is fed into the machine, and then piece is cut to length. So here you can see what I described earlier with bolts and screws. Thread rolling is another approach used. So with upset forging operation, which allows you to form a head on a bolt or similar hardware item, the cycle consists of the following. You have the feed, the wire stock feed, and then you have the stop here, right? And here's the two dies here, the dies, and the punch. So what I'm going to do, I'm going to bring the grip dies together, and then I have the stop that will be removed. It's retracted. You can see that there. And then I'm going to bring the punch next, which moves forward. And as that's pushed forward, it basically constrains all that volume into this rectangle, creating the bolt head. So that's what we're talking about here. That's your bolt head. The blank goes in here now. And you can now create your threads through thread rolling. Here you have the upset forging. You can actually have the punch. So that's A. So the heading nail uses an open die. Here you have a round head formed by the punch. And then here you can see two common head styles for screws formed by a die in this case. And then here's a carriage bolt, which is a head formed by a punch and a die. Trimming is a cutting operation to remove the flash from the work part in the impression die forging. It's usually done while work is still hot because it makes it easier. So you have a separate trimming process at the forging station. And so here's your flash, your die, and your punch. And now I can apply a trimming operation to remove that flash. It could be through shear, possibly. Extrusion, so you have two types. I discussed this already. It's similar to squeezing a toothpaste out of your toothpaste tube. In general, there's types of parts that can be made: direct extrusion or indirect extrusion is used to produce very long parts with uniform cross section. So here you can see the ram. I already covered it, but I'm just kind of going through it one more time. You have direct extrusion. I'm applying a force to this ram. Here's your work billet. Here's your die, and I'm pushing this through to get the final work shape. This is also called the forward work extrusion. As the ram approaches the die opening, you do have a small portion of the billet that remains that cannot be forced through a die opening. We call this butt. This extra portion called the butt must be separated from the extrudate. And so you have to cut it beyond this exit, otherwise you're going to be stuck with that. So yeah, that's one issue with this approach. The final shape of the extrudate is determined by that die opening that we have here. It could be square, a circle, you can decide, but you're going to have to cut it. You can also create hollow shapes with these processes by using an interior mandrel. And so that allows you to get semi-hollow shapes. So here you can get a circular, square, a C shape. And then indirect extrusion here allows you to produce a side cross section and a hollow cross section. So you can do that. Here's your die. In this case, here's your work billet, your container. Here's your final work shape right here, right? That you can get. Here's your container, your work billet, your die, and the final work shape. So comments on indirect extrusion is also called backward extrusion and reverse extrusion. The limitations of indirect extrusion are imposed by lower rigidity of the hollow ram and difficulty in supporting extruded product as it exits the die. So what is the advantage of extrusion? You can make a lot of different shapes, especially if you use hot temperatures. The limitations: part cross-section must be uniform throughout the length. The grain structure and the strength are enhanced in the cold and warm extrusions. Close tolerances are possible. Very little waste with this approach. With extrusion die features, I want to show you a few things here. You have the die angle that can be very helpful to understand. Here's your container, and there's an effect of the die here with the ram force. So with increasing die angle, so this angle increased, you may need a higher ram force. So there's an optimal value at which you can actually apply less force and yet get the part you want. So I have some comments on the die angle. Low die angle does give you surface area that's large, but it does increase friction at that die to billet interface. So you get a higher friction, means you have a larger ram force required. Now a larger die angle has more turbulence in the metal flow during the reduction process, and the turbulence as a consequence increases the ram force required. So there is an optimal angle depending upon the work material, billet, temperature, and lubrication. And the way you can precisely determine these is through experiments. So what about the orifice shape of the extrusion die? The simplest cross-section that can be made is a circular die orifice. The shape of the die orifice affects ram pressure, and as the cross-section becomes more complex, higher pressure and greater force are required. The effect of the cross-sectional shape on pressure can be assessed by the means of something called a die shape factor Kx. So this is something that people use to be able to do that. Now here's a complex cross-section that was extruded. And you can see here, this was used for heat sink. The orifice shape of extrusion die, we covered that already. And here is, you probably have an extrusion die shape that was very complex for that. Now, you have wire and bar drawing, which we also discussed or earlier. You're pulling the material through the die opening. So here's an example here at the top. Similar to extrusion, but I'm pulling it through the die. That's the difference there. And that's applying tensile stresses. But compression also forms because here this work is pushed against this die, and that's in compression. So the material is getting squeezed as it's passing through the die. So here you have my initial diameter, the final diameter, the force applied. This is your final work size. This is a draw die, and here's your length of contact. And that's your angle there of that die. So what's the difference between wire drawing and bar drawing? The difference between bar drawing and wire drawing is stock size. The bar drawing is a large diameter bar and rod stock, while the wire drawing is a small diameter stock. Looking at 0.01 inch is even possible with these approaches. You can get very small wires. Although the mechanics are the same, the methods are different. Now, you can produce a lot of things here. Usually you can do this through cold working, and most frequently we use it for round cross sections. So some examples: electrical wires, wire stock for fences, coat hangers are made this way. If you've seen the wires in a shopping cart, those are made the same way as by doing this drawing approach. Rod stock for nails, screws, rivets, and springs are also made very similarly. And here you can see bar drawing accomplished in a single draft operation. The stock is pulled through one die opening, and then you get your straight cylinder. It does require a batch type operation. And here you can see the bar drawing bench. Here's your hydraulic cylinder, the carriage here, right? And here's your drawn bars. You're drawing the bars. Here's your die stand, and here's your starting work material. That's my entry table I'll be using. I feed the starting work material, getting pulled through this carriage and hydraulic cylinder that has enough power to be able to pull it through. So wire drawing, the continuous drawing machines can make multiple draw dies. Annealing may be required, in some cases to relieve the work hardening. And here you can see continuous wire drawing, where not only have the initial wire stock drawn through that die, I can have another one going through another die, and I'm pulling it to have a more and more wire thickness reduced. You can see it's thicker here, and thinner here. So I invite you to watch this YouTube video here at the bottom that shows a high-speed wire drawing process. With that, I want to thank you for your attention to the